Let's look again at this table here. This table shows different fuels, basically different hydrocarbon fuels, and some of their properties that could help us determine their combustion efficiency. So fuels include something like acetone, acetylene, benzene, butane. Some of these fuels are gaseous, some of them are liquid, and they do have different properties, including the molecular weight. Basically, this is how much grams in every mole. This you can calculate from the molecular structure. So for example, if you get C6H6 for benzene, so this will be 6 carbons and 6 hydrogens. You add them together, the molecular weight of each of them. Heat of vaporization, how much BTU you can get per pound of vaporization. Heat of combustion, which is a much higher value than the vaporization. This is when you burn them, how much heat you can recover. And this is in BTU. BTU stands for British Thermal Unit per pound of compound combusted. You can see that it varies from 17,000, around 17,000 for the toluene, 17,000 for the benzene, up to 50,000, for example, for hydrogen. Hydrogen is one of the ones that really have very high combustion energy. So basically, when you burn it, you get so much energy out of it. And being small, one of the most smaller molecular weights, meaning that you can, with the same weight of hydrogen, you can do much, much more energy than you can do from a lot of other compounds. Stoichiometric mixture volume. This is how much with stoichiometry you need from air to burn each of them. Remember the formula that we started with, that the hydrocarbon will react with the oxygen. So you do need oxygen, and oxygen comes from the air as 21% by volume. If the oxygen is 21% and we need this amount of oxygen, you can always calculate based on the equation that we put earlier, the chemical reaction of combustion, and you can calculate based on stoichiometry how much volume of air is needed. For example, we have to let this air goes. If your car is fueled by methane, you need to let more than 9.48% of air in so that you can get complete combustion of the methane in your taxi in Abu Dhabi. Then we do have explosive limits, and I'll talk to them about them in a minute. We have the lower explosive limit and the upper explosive limit. Other words for them is lean burn and rich burn. These values as a percent of this of the fuel, you get spontaneous ignition temperature. This is the temperature where it can, above which it will burn by itself. So beyond this number, you can have self-ignition, and very big good example of that is landfill sites where anaerobic reaction happens and methane is being generated. At some particular temperatures, it starts already to burn by itself. For example, the methane auto-emission temperature is negative 1170. That means that at room temperature, it will burn on its own without, it does really not need a flame to burn. If it is there at specific concentration, and to give you a hint, this concentration needs to be between 46 and 164, as I'll talk about them in a second. So the heat of combustion. The higher heating value assumes combustion water is condensed, thus giving up its latent heat to condensation. The lower heating value assumes combustion water leaves as a gas. The lower value is less than the higher heating value by the amount of the latent heat of condensation. And then we do have the lower and the upper explosive limits, which is the lean limit. At the lean, below the lean limit, you really don't have enough hydrocarbons present to sustain the combustion. Above the explosion limit, which the UEL, the rich limit, there is too much hydrocarbon also to sustain combustion. So let's look at some numbers. What are the stoichiometric mixture lean limit, LEL, and rich limit, UEL, for the combustion of methane in air? According to the table that we had earlier, methane and air, they have stoichiometric mixture contains of 9.48% by volume. The lower explosive limit for methane is 46%, and the upper explosive limit is 164%. So we multiply the mixture volume percent by the lower limit, we get 4.36% volume to 15.55% volume. This is our range. Now let's calculate the weight percent of methane. The weight percent of methane is 0.095, which comes from the percent volume, times 16, which is the molecular weight of the methane itself. That's one carbon is 12 and four hydrogens are 4. So let me just write it down for you here. This is the 0.095. This is the percent volume. Now you get your 16. This is one carbon, which is 12, plus 4 hydrogen. Each is 1. That gives you 16. And we'll divide that by the total, which is the 0.095 times 16. That's for the methane. Now we have 0.905, which is the rest, times 29, which is the average. 29 is the average molecular weight of air. That, how do you calculate that? 79% times the molecular weight of nitrogen plus 21% times the molecular weight of oxygen. You get 29. And the molecular weight of nitrogen is 28. The molecular weight of oxygen is 32. So we do this calculation. We get that the total weight percent is 0.055, which is 5.5 weight percent. Gas compositions in combustion are stated as volume percent, same as mole percent. However, in few cases, the weight is used. Automotive engines, for example, use air-to-fuel ratio, which is pound per pound. And if you're into cars, you should be very familiar with this ratio. That's something for that specifies the engine. For methane, a stoichiometric ratio, we compute that the ratio assuming that we have 1 mole of fuel-air mixture. So we do have, this is 1 minus 0.0948, which is 0.905 times 29 over 0.948 times 16. So it's just this part. It's this part over here. Just let me get the cursor again, or I can just do it by the pen. So it's this part over here divided by this part over here. And that will be your air-to-fuel ratio in pounds per pound. So looking here at this graph, we get on the x-axis the percent or the fraction of methane in the air, and on the y-axis we get the temperature. So we can see that on this we have 2 main limits. We do have the lower explosive limit here in red, and we have the upper explosive limit. So between these 2 values, we see that it is flammable. Above that, it's too rich to burn. Below that, it's too lean to burn. And the temperature will keep rising, keep going up until it reaches the maximum at stoichiometric ratio. So the maximum really happens when you have just enough balance in the reaction to balance your fuel together with the air that's inside. So methane mole fraction is less than stoichiometry. That means all methane burns, temperature rise is dependent on the amount of methane. Methane mole fraction is more than stoichiometric. All oxygen is used. Temperature rise depends on the amount of oxygen. If the concentration is in this part, where is lower than the LEL, the mixture is too lean to burn. Above the UEL, the mixture is too rich to burn. The computed temperatures at the two limits are quite different, and this is about 2000 to 3000 Fahrenheit. Most hydrocarbons temperature at the LEL is about 2300 to 2400. That's not particularly for methane. That works for all hydrocarbons. And the temperatures at the UEL are generally higher and less uniform. The flammable region becomes wider if the gas is preheated. The values regularly shown are mixtures at room temperature. That's why in cars you will find that we are trying to heat the fuel going in before it's injected. So mixing in combustion reaction, we can see in this figure over here that on the x-axis we get the air to fuel ratio, and on the y-axis we have the percent by volume. Let's look at the oxygen. The oxygen in the left part, we have deficiency because we don't have enough oxygen to support your combustion. The more air to fuel ratio you get, the more oxygen. You see this part here, and I try to do it in another color. So the oxygen, let's put it green. Here this one is, or blue, sorry. This is the oxygen. This one. So, or the dotted one. Now, let's look at the CO and H2. The CO is a byproduct of incomplete combustion, so we can see always that it will differ based on how much oxygen and what's the temperature. So the higher the temperature, the lower CO we will have. So we can see here that the CO is going down. That's in green here. And this is CO and hydrogen going out. So also the CO2 will be maximum when you get the least CO. So the maximum will be at the higher temperature, which happens exactly at the stoichiometric mixing. So let's do it in dark blue. So this will be my CO2. Now we can see that ideally, which is the dotted ones, all the dotted ones, ideally everything will be CO2. So that's why we have the orange one. This will be your ideal CO2, which does not really happen in reality, but in reality some of it is converted into CO and so on. So we'll stop here with this video, and next video we'll be talking about flame temperatures.